Assalamu alaikum, respected faculty members. I am Mohammad Asiful Islam and I will be presenting this video on behalf of our team, Project Hexabit, for the EEE 4308 course. You can see the details of our 7 group members displayed on the screen. In this digital snake and ladder game project, we apply the theoretical concepts learned in EEE 4307 to recreate the classic snake and ladder game using digital electronics. Let's get started. Project overview. There are many different components that come together to make this game operational. Let us go through them one by one. Firstly, the dice module. This generates random numbers 1 to 3 using 555 timer-based clock. The number is displayed on a 7-segment display. Next, the board module. The game board has 16 blocks numbered 0 to 15. Each block has 4 colored light LEDs to show different parts of the game. Player 1 in red, player 2 in blue, snakes are yellow, and ladders are green. The blocks are arranged in a neat 4x4 grid, making the board easy to see and to use. These are the different colors of the LEDs. Next, the snake and ladder logic module. This implements the rules for snakes and ladders, ensuring the players are correctly repositioned when landing on a snake or ladder. Next, we have the player selector. This module allows the selection between the two players. Player 1 is shown in red, player 2 is shown in blue. Next, the game memory or memory module. This module allows this module keeps track of the current position of the players and updates their positions when a snake or ladder is encountered. Next, we have the reset module. The reset module provides a means to reset the game to its initial state, restoring player positions without turning the whole game off. Next, we have the decoders. These include the player decoders, the snake decoder, and the ladder decoder. These determine the current position of each player, snake, and ladder and updates the board accordingly. Finally, we have the winner module. This module declares when a player has won the game by reaching the end. A buzzer and an LED indicate the winning player's corresponding light. Now let us discuss each of these modules individually, starting with the dice module. A 555 timer IC is used here that generates clock pulses which are rapid on and off signals when the player presses a button. When the player releases the button, it displays a number among 1, 2, and 3. It acts as a pulse generator to make the dice roll. A 4017 Johnson counter is used, which receives the clock pulses from the 555 timer and cycles through the numbers. In this dice circuit, the 555 timer operates in astable mode when the button is pressed and shifts to monostable mode when released. In the snake and ladder game, only numbers 1 to 3 are needed. Therefore, only the first 3 outputs of the Johnson counter are used, and by using a combination of diodes, the input is given to a binary coded decimal to 7-segment display decoder, which then sends it to the 7-segment display. The switch we used in this module is not an ordinary switch. If we were to implement this push button physically, we would need debouncing due to mechanical vibrations of the metal contacts, which could cause false triggering of the dice roll. To eliminate this, a debouncing circuit is used with a Schmitt trigger and a low-pass filter. To achieve smooth switching, use a Smith trigger inverter represented by the 7414 IC. Its key feature is hysteresis, meaning it has two different threshold voltages. Any voltage between these thresholds results in no immediate change, preventing noise from causing false triggering of the dice roll. The output will be slowed down to show clear operation.
This is our dice module. Initially, the value of capacitor here is 5 microfarad. So if we run the simulation, we can see the dice value changes very fast as the frequency is very high. So as we want to decrease the frequency, so we have to increase the capacitor value. If we make it 50 microfarad, the time constant will increase and it will decrease the frequency. Now the dice value is very slow and we can take the dice value as much as we want.
Now we move on to the snake ladder logic module, which will receive input from the memory, the current layer position, and the snake ladder head, ladder tail, snake head, snake tail from their corresponding decoders and the dice value. We didn't take the length as input because we had already calculated them in their decoder modules. So we just took the tail for the snake and the head for the ladder as input instead of their length and calculating again. Now let's move on to the child sheet. Hmm. We can first of all we add the current pair position with the dice value gotten with the 4-bit adder, and then after we have added and calculated the updated position, there can be four distinct cases. First, the general case in which we don't encounter any snake or ladder, and the value is within the board maximum value. So we in this case we just update the value according to the updated position gotten from the error. Then we have the snake tail case where we encounter a snake, the updated position will be the snake tail and the ladder head. Then we encounter the ladder, so the updated position will be the ladder head. And the present position, in this case, the value gotten from the error is more than the board can handle. So in that case, we just keep the present position. The player doesn't win either. So how does the internal mechanism work? We use a priority encoder to find out which case it actually is. First of all, we see if there's any carry out from the error. If there's a carry out, we don't change the position. So, which is we send the input to the it of the and since it's a priority encoder, if this value is zero, the others won't matter. So for 8 we'll get here 1 0 0 0. So this line will activate and this will go to the present position. So we don't update the position. Now next we have the snake case and the ladder case. Now out of snake and ladder, we were instructed that the ladder will take priority. So in number 4, we send the ladder comparator. We compare the updated position with the ladder and see if it's uh, matching with the ladder tail. And if it does match, we'll have 0 here. So the other ones matter in that case, and the ladder will take priority. And when we have the snake comparator will compare with the snake head and give 0 here. So we'll have 0 and the others will matter. And if it's none of the other case, we can presume it's the general case in which we just update the player position based on the value gotten from the error. One thing that needs to be mentioned about this priority encoder is that the inputs were chosen so that there's only one high in the output. Let's say for 8 we'll have 1 0 0 0, so that's only one single one in the output side, and for 4 we have 0 1 0 0, so that's only single one in the output side, and for 2 we have 0 0 1 0, which will also have single one in the output side, and for 1 we have 0 0 0 1, so just that as well. So by choosing that we can now filter them out with AND gates. Now Q3 is AND gated with the present position because Q3 will be activated when there's a carry out, and Q2 is and gated with the ladder hit position because it corresponds or it will be 1 when we have encountered the ladder, and Q1 is and gated with the snake tail because it will be 1 when we encounter the snake, and the Q0 is and gated with the jet with these 4 gates because it represents the general case in which we only update the position based on the value gotten from the error. After we have determined the actual case, we can pass the same bit positions to a OR gate to get the actual output for that bit. And so we have 4 bit in total, so we get the 4-bit updated position. And this OR gate serves a different purpose. First, when we began the circuit, I thought we could say, use the dice phase signal for both the trigger for passing the dice value and the pre- present value to the adder, so we can calculate and use it for the updating of memory position as well. But to see the time delay, there's a time delay for calculating all these cases, and so the memory position update fast, so we cannot have that. So in order to combat the delay, I added an OR gate which will only output the one after a calculation has been done. So we if as the clock pulse for the memory, so we can have the both the updated value and the pulse for that at the same time. So that's that. Now for demonstration, we have placed both the snake and the ladder position in the 8th position. So now since the dice value is already 2, we can add 6. Now once 6 has been added, we have about 8. And since both of them, both the snake and the ladder at the 8, we have ladder taking priority, which we can see here. Then it goes to the ladder head. The next position we have a ladder head, and which is 1100 at the 12th position. Let's confirm if it checks out the actual decoder. Here we can see the ladder tail at 8 and a length of 4, so we have 12. So our result checks out. So that's it. The player selector will provide 0 for the red player and 1 for the blue player. And now let's move on to the memory module. The memory module will take some input, first the updated position, which is calculated from the SL logic module, and the carry out, which is also coming from the SL logic module, and the dice press signal, which is which will actually, whenever we press the dice, we'll have 0. After releasing the dice, we'll have 1. And for player selector, it is coming from the player selector module. As you can see, it's the red player, and we are receiving 0 here. And the master reset switch is supposed to reset all the registers used in the memory. Now let's head into the memory. Now, first of all, we have all the inputs, then, and we have two registers for two players. This is for the first player, red player, and the second player, the blue player. And how do we calculate? Be- Before checking out how the appropriate register is updated, let's check out how player positions are sent to the SL logic to calculate the updated position. Let's see. We can see there are 4 AND gate for each register. So we have two register, and there's two additional inputs for each AND gate, which will be one the player selector and other is the dice play signal. Whenever we place the dice, we don't want any input sent to the SL logic because the dice is continuously changing the value. So uh, whenever the dice is placed, we have 0, so the value, none of the values will be passed. So when we release the dice, there will be 1, so we can say the value will be passed, but we have to pass the value for the appropriate player. That's why the player selector comes in. So since the player for the red player we have 0, then we invert it to 1 and send to all the AND gate for the first player, the red player. And the inversion of that is sent to the second player. So it's only one of the player's position is sent to those AND gates, and their corresponding bits are OR gate sent to the OR gate to get the actual 4-bit output. Now, after we have seen, now let's see how their registers are updated. First of all, their clock is, as mentioned previously, the carryout works as the clock because the carryout only gets 1 after we have calculated the updated value. So we have sent that carryout to the OR gate. Now we have to choose the appropriate player register. As well, again the player selector value comes in. So we OR gate with the player selector, since player selector is, let's say, 0 for the red player. So we have 0 here. So only when the carry out changes, it will matter. But for the other OR gate, we the inversion of player selector, which is 0, so 1 will be passed here. So even if the carry out changes, it will matter because it's the OR gate. So after the player toggles, then it will become 1 and this will become 0, and then only it will matter for this OR gate. Then we can change the for blue player as well, and it will continue after each toggle. So that's how the memory works. Now for testing the memory and reset module, we can see the initial values in the register are not 0, so we press the reset module, and which will lead back to the all the 0 position. Now after we have reset, we can see also the player is now the red player, which will be our first player always. Now after Now, how will the memory update? Let's see. And when we press the dice, we'll have a 0 signal. So let's say we have pressed the dice and we have a 0 signal here. And after we release the dice, the calculation has been done and it will be sent a 1 here. So 1 is sent here, and you can see the player position is been updated for the first player. And so after 1 opinion, we can see the player has been toggled as well. So after the player is toggled, now we again place the dice, then release the dice, and the position has been updated for the second position player for as well. And now it's the first player's turn. So that same value, not the same value, but the which is the same value for the player one as well, and it is passed for the next calculation. So that's how they work in Interact.
If we check the output of the individual modules for snake decoder module, we give input of the snake head and the snake length. Here we have given the input of snake head to be 1101, that's 13, and the length is 1001, that is 9. So the snake head should be at 13 and the snake tail should be at the subtracted result of these two, which is, we can see over here, which is 4, 0, 1, 0, 0. And this is shown in the board module. We can match the output. In the board module, we can see the yellow snake. The snake head is at the 13th position and the snake tail is at the 4th position. That makes the snake length 9. Now if we look at the ladder decoder, the ladder start is given as, suppose, 3, and then the length is 7. If then the ladder top or ladder end should be the added value of these two binary numbers, which is 1010, corresponding to decimal 10. So in the board module, the ladder start should be at the 3rd position and the ladder ends at the position 10. Now from the memory, we get the player positions for player 1 and player 2. Here we can see the positions are at 0 position. These data are transferred to the player decoder modules. The inputs here are all zeros, so the output of the decoders are can be represented at the board module, and we can see that both at 0th position.
Now for the complete integration, we have the board module which takes inputs from the air position decoders and the spectral logic spectral decoders. And we have the LEDs here. So first we provide input to the snake decoder and the ladder decoder. So let's start the simulation, and we we provide for the snake decoder the snake head and length, and subtract that we have the tail. And for ladder decoder we have the ladder tail and length, and at that and we have the snake head. Now snake head and snake tail and ladder tail and ladder head both are fed input to the signal logic module, and we can see that their inputs are coming here. And we have additional inputs which are the current player position and the dice value from the dice module. The current player position is be determined by the memory which is coming from, let's see, here is the current player position, and which is the current player. It will be determined by the player selector module, and working with the memory, and the memory will send according position the current player for the current player. And after the position is sent here with the dice value added, we can determine the updated position, the new positions here, and which will be then sent to the memory. You can see the wires are coming here, and we have the updated position here. And after the updated position has been updated, and it will automatically toggle the player, and we'll have the current position for the next player as the input for next dice press. So which will be then updated again with the dice value, and we'll keep repeating. So that's how the integration will work. The memory sends the positions for both the players. You can see both the players to their corresponding decoders here, and the decoders light up the LEDs according to their position. And as for the snake and ladder position is the board module. They are sent from the snake decoder and the ladder decoder. Now for the winning module, we have it at the corner, and we can see its input will be the player positions. The one for the first player, one for the second player, which will use AND gate. And we know for position 15, it will be all four will be one. So when four becomes one for any of them, it will light up their corresponding LEDs, and there will be a buzzer, so we can understand which player wins. So that's how the complete integration works.
We had some special design considerations. We used debounce circuits for push buttons in reset and push button of dice. These debounce circuits are used to eliminate the bouncing of the mechanical switches that may cause false triggering in the reset or false triggering in the dice. Is the reset push button with debounce circuit. And here is the dice push button with its debounce circuit. Another consideration is to use the 555 timer IC in the astable mode. When we want to roll the dice, we need high frequency clock signal to rapidly change the dice value. To serve that purpose, the timer IC is configured in astable mode, so as long as the IC gets power, the output pin keeps oscillating between high and low voltage, and every pulse ensures positive edge triggering and changing the dice values. An important design feature lies in the generation of clock signal for the memory. We are taking a signal from the snake ladder logic and giving it as input in the memory. So if we enter the snake ladder logic, we can see we have used a 4-input OR gate. So whenever the dice button is pressed, it makes all the current player position inputs 0 for the logic module, and these 0 inputs cause 0 output in the module, and thus the clock signal that we were using for the memory stays low. And when the dice button is released, the current player position gets a value, and the output gives a new player position which has a value, and that value makes the OR gate output high. And when the OR gate output gets high, it gives the positive edge triggering to the memory module. Now if we go to the memory module, we can see that we have used the clock signal here to give the clock signal to the memory ICs to update the new player position for the corresponding player. So the same clock signal that we're getting from the snake ladder logic used in the memory, we also use it in the player selector module. This gives it an auto toggle feature. So whenever the dice button is released, so the JK flip flop in the player selector module gets the clock pulse and toggles the selected player.
Now for playing the actual game, first we will reset the any initial value we have. So we are back to 0, 0 position, which you can see on the board module. And we have set the uh, both ladder tail and snake head at the position edge, so we can verify actually if ladder takes priority or not. So we have both of them are length of 4, so subtracted, and we have the new position for in case you encounter snake, which will be at 4, and in case you and the ladder position will be at 12. So obviously ladder will take the priority first. So we play the game. First we have initially at set position 0. So Let's play the die. And yes, the red is the first player, so it has moved to LEDs. Then for the blue has moved 3 LEDs. The red has moved one. The blue has moved one. Red has moved one. Okay, so after 3 moves ahead, we had the ladder position. So the blue player has moved up in the ladder. Okay, it's only one. It's like the blue will win. Okay, he has gotten the ladder as well. Okay, so we have the blue player winning. So let's see if the winner module work correctly. Yes, we can see the blue light is on, so the blue player has won the game.
Thank you for watching our video presentation. We hope it was satisfactory.